Good morning, students. In this session, we will learn about data processing, which is a fundamental step in transforming raw data into useful information. Data processing enables organizations to make informed decisions, discover patterns, and generate valuable insights. We'll explore different stages of data processing, data cleaning, duplicate removal, and outlier detection. Data processing refers to the transformation, analysis, and interpretation of raw data. The objective is to convert unstructured data into meaningful information that supports decision making. In IoT systems, data processing is particularly important because sensors continuously generate large volumes of data that must be analyzed efficiently. Data can be classified into structured, semi-structured, and unstructured forms. Structured data is organized in tables and databases. Semi-structured data includes formats such as XML and JSON. Unstructured data includes text documents, images, videos, and social media content. Understanding the data types helps in selecting the suitable processing techniques. Data can be collected through surveys, sensors, databases, web applications, IoT devices, social media platforms, and transactional systems. The quality of analysis depends heavily on the quality and accuracy of the collected data. After collection, data must be stored securely and efficiently. Common storage solutions include relational databases, cloud storage platforms, data warehouses, and distributed storage system. The choice of storage depends on the data volume, speed, and accessibility requirements. Raw data often contains errors, inconsistencies, duplicates, and missing values. Data cleaning improves the data quality by removing inaccuracies and preparing data for analysis. Proper data preparation ensures reliable results and better decision making. Data analysis involves extracting meaningful information from datasets. Common techniques include descriptive analytics, diagnostic analytics, predictive analytics. These techniques help the organizations understand the trends, predict the future outcomes, and optimize decisions. Visualization helps transform complex data into understandable charts, graphs, dashboards, and reports. Visual representations enable the users to identify trends, patterns, and anomalies more effectively than raw numerical data. Several tools are available for data processing. Excel is widely used for basic analysis and reporting. R is suitable for advanced statistical analysis. Python provides extensive libraries for data science and machine learning. SQL is used for managing and querying a relational database. Each tool serves different analytical needs. Big data refers to extremely large and complex data sets that cannot be processed using traditional methods. Technologies such as Hadoop, Spark, and cloud computing enable the efficient processing of large scale data generated by IoT systems, social media, healthcare systems, and industries. Data processing must follow ethical principles such as privacy, security, transparency, fairness. Organization must protect personal information, prevent unauthorized access, and ensure responsible use of data. Data processing is widely used in healthcare, finance, education, retail, transportation, smart cities, and IoT systems. Organizations rely on processed data to improve the efficiency, reduce the cost, and enhance the customer experiences. Emerging trends include AI, ML, edge computing, real-time analytics, cloud computing, and automated data processing. These technologies are transforming the way organizations manage and utilize data. Data processing converts raw information into actionable insights. It improves decision making, enhances operational efficiency, and enables organizations to leverage the full value of their data assets. Handling missing values. Missing values occur when information is unavailable or not recorded. These missing entries can affect the data quality and lead to incorrect conclusions. Therefore, identifying and handling missing values is a critical step in data processing. Understanding the missing values. Missing values can arise due to data entry errors, equipment failures, communication issues, or incomplete surveys. Understanding why the data is missing helps determine the most suitable treatment method. Imputation refers to replacing missing values with estimated values. Common techniques include mean substitution, median substitution, mode replacement, regression-based estimation, and edge learning approaches. The choice depends on the nature of the dataset. After imputation, it's important to evaluate the impact of data quality. Visualization tools, statistical measures, and consistency checks help verify whether the imputed value perceive the original characteristics of the data. Preserve the original characteristics of the data. Best practices include understanding the cause of missing data, selecting appropriate imputation methods, documenting the pre-processing steps, and validating the results before analysis. These examples demonstrate different approaches for identifying and treating missing values. Students should observe how various techniques influence the dataset completeness and analytical outcomes. Removing the duplicates. Duplicate records occur when the same information appears multiple times in a dataset. Duplicate removal improves the data quality, reduces the storage requirements, and ensures accurate analysis results. Common techniques for duplicate removal. The duplicate records can be identified using exact matching, fuzzy matching, and conditional matching methods. The appropriate technique depends on the nature of the data and business requirements. Not all the duplicates should be removed. In time series datasets, repeated timestamps may be valid. Multiple measurements of the same event may also be legitimate. Therefore, understanding the context is essential before deleting the records. Duplicate removal becomes difficult when dealing with inconsistent data formats, large datasets, spelling variations, and incomplete information. Proper duplicate detection strategies are required to avoid accidental loss of valuable data. Best practices include defining clear duplicate criteria, validating the results after removal, maintaining the backup copies of datasets, and documenting the pre-processing activities. These examples demonstrate exact matching, fuzzy matching, and conditional duplicate techniques. They show how duplicate records can be identified and removed while preserving meaningful information. Outlier detection. Outliers are the data points that significantly differ from majority of observations. They may result from measurement errors, unusual events, or genuine rare occurrences. Detecting the outliers is important because they can distort analytical results. Importance of outliers. Outlier detection improves the data quality, enhances the model accuracy, and helps identify abnormal events such as fraud, equipment failures, network intrusion, or medical anomalies. Common outlier detection techniques. There are several techniques that are used to identify the outliers, including statistical methods, Z-score analysis, interquartile range (IQR), clustering methods, and machine learning algorithms. Each technique has advantages depending on the dataset characteristics. Challenges in outlier detection. Outlier detection faces challenges such as high dimensional data rate, context sensitivity, and limited sample sizes. A value considered an outlier in one context may be perfectly normal in another. Strategies for handling outliers. Once detected, outliers can be removed, corrected, transformed, or retained depending on their significance. The decision should be based on domain knowledge and analytical objectives. Applications of outlier. Outlier detection is widely used in fraud detection, cybersecurity, predictive maintenance, healthcare diagnostics, quality control, and financial risk management. Visual techniques such as box plots, scatter plots help